Okay, welcome to class 2 of networking communication. And today we're going to talk about a form of communication called asynchronous serial communication. And I'm also going to mention the lab assignment number 1, which is posted on the course page as well. All right, so let's go ahead and get started. So the first thing is a quick review. We had kind of finished up with this concept that Emile Baudot had created that was called 5-unit code. And there were a number of things that were remarkable about the invention that Baudot had created. And one of them was that it was the first use of kind of this binary serial code to encode a number of different symbols. In other words, we're taking a symbol like, I don't know, let's take the letter A down here, capital A, down here. And the idea was, well, I can take that A and assign it this pattern of off, on, off, on, off, and then I can send that over to the other end. But rather than using 5 wires to do that, he used 1 wire, and the way he did it was by having each bit go on the line one at a time. And back then, this is quite a while ago, so back then it was not done electronically or with electric like computer devices or anything like that. It was done with this mechanical and electrical thing, or an electromechanical system. They had these rotating rotors. So on the transmitting end, you would latch in the number you want. So for letter A, 0, so you leave that one off. You turn this one on, so 0, 1, off, on, off. So 0, 1, 0, 1, 0. You latch those 5 switches in. In the early systems, there's actually like a 5-key keyboard with 2 fingers and 3 that you could type with. And then later on, it actually had a physical keyboard that when you press the letter A key, it latched that pattern in automatically. So the A key would push just this one and this one down. The B key would push this one, this one, and this one down. So each key had its own pattern of switches that it would put here. Well, the idea is when you would put that down, this rotor would spin and it would hit the first position. So right here, you can see the arrow showing the way that it spins. So that would make contact between here and the wire. So the first switch, if that was on, that voltage would go onto the wire. If the first switch was off, then no voltage would go onto the wire. And that would, as this rotates, imagine this rotating like a hand of a clock, but a little bit faster. So it would go like click, and then you would have the first bit, and then that one would fall off the contacts here, and then click, second bit, click, third bit, click, fourth bit, click, fifth bit, and then we're back up to here in the center position. On the other end, there's a rotor that's rotating in the same position at the same speed. So when this one is on the first bit, or bit 0, this one's on the first bit, and that latches that into this thing. So when this completes a rotation, the pattern on the switches here would be copied on these little latches over here. And so now we've transmitted those 5 bits, but they've gone across one single wire by using that line 1 bit at a time. Now, one thing about that is if we toward the end of the lecture last time, we looked at this general concept of you have a source, you have a destination. Well, to get the data from the source to the destination, which is what communication is all about, we have to have it conveyed somehow across something. So there's a channel. And we have to have a way to get the data onto the channel. That would be the transmitter. A way to get the data off of the channel. That would be the receiver. And pretty much every communication system falls into this kind of abstract model of how communication works, like talking to somebody. You have an idea in your head. The transmitter is your vocal cords, which vibrate as air goes through out of your lungs. That then induces the compressions and rarefactions in the air molecules as the channel. The receiver is the ears, which receive those vibrations. They have a bunch of little hair-like structures inside of there that are connected to nerves. And when that vibrates, the eardrum vibrates, it wiggles, there's a little bone linkage that wiggles that, and the vibrations are transmitted into that like a kind of a spiral-shaped organ in your ear, and it wiggles those little things, and those nerves then go into your brain, and you hear that. And now the idea of what this person is trying to convey now goes into the other person's head. But notice that we have a transmitter, we have a receiver, we have a channel, we have a source, we have a destination. And if we were to take any of these out, this chain wouldn't work. So for example, somebody who is hard of hearing, their receiver doesn't work properly, you can't really talk to them using audio. Or if you're in a vacuum or a place where there's so much channel noise, a really loud concert venue, for example, then you can't pick up the data because there's too much noise. Or somebody who has something wrong where their vocal cords don't work, they can't talk. Or there's another thing as well. There's another layer here that's understanding the message and getting from an idea to another idea. If they don't speak your language, or their receiver works fine and your transmitter works fine, but they don't have the way to do anything with that message to convert it back into that idea because they don't speak the same language as you. So the idea here is every communication system works like this. Now in Baudot's case, let's go back to that. In Baudot's case, the channel is that one wire. The transmitter and receiver are those things that look like distributors that spin, that make contact between the different things, like this. The source is the switches on the input. The destination are the latches on the output. Now, that is a form, Baudot's system was a form of what's called time division multiplexing. In other words, we have 5 bits, but only one wire. So how do we fit 5 bits worth of data onto one, or 5 switches worth of data onto one single wire? And the answer was, well, have them divide up the time and have each bit on there for a certain amount of time. So as this rotor spins, it's going to be on this little kind of rotor cap, the little contact, will be on bit 1 first. And as this spins, it'll be for some amount of time. And then it will hit bit 2, and then it will hit bit 3, and then it will hit bit 4, and then it will hit bit 5. But notice as that spins, it can't be on ever 2 of them at one time. It'll always be on 1, and then a little break, and then 2, and a little break, and then 3, and a little break, and 4, and a little break, and 5, and a little break. And then over here, these are drawn to round out the circle, but these aren't really contacts right now. And then it will spin around, and then by the time it gets back around to here again, then we have bit 1, 2, 3, 4, 5 again. Bit 1, 2, 3, 4, 5 again. And on the other end, this has to be synchronized. But as this goes, when that one's on 1, this one's on 1. When that one's on 2, this one's on 2. And so forth as those rotate around. Now, that is called time division multiplexing because we're multiplexing means we're putting more than one piece of data on one line or on a smaller line. And it's time division because each one of those bits has its own time slice that it's using the line for. Now that for that to work, the transmit and receive rotors on each of the 2 ends have to remain synchronized. So in other words, if I'm on 1 here and this one is way before 1 over here, then the data is not going to get through in bit 1. Or if this one's on 2 and this one is behind and it's on 1, then bit 2 will be misinterpreted for 1 and so forth, and the data will all be garbled up and we'll get the wrong message. So for this to work, those have to remain synchronized as the rotors turn on each of the 2 motors on the 2 ends. Now, they don't have to be perfectly synchronized, but they have to be close enough that when this one's on 1, that one's on 1 for a period that doesn't make it so when this one's on 1, that one's on 2, or when this one's on 1, this one is before 1. So it has a little bit of ability to have some variance here, but it can't be wildly off. All right, so what happens if the rotors get out of sync? Well, we talked about that. If the rotors get out of sync, the bit pattern might be just not there. For example, if this one is on the message, well, this one is on these blanks. Or if this one's on, or it could be corrupted. If this one's on 1, well, that one's on 2. It's all off one way. Or if this one's on 2, well, this one's on 3 or 1. The bit pattern will all be shifted over one way or the other way. So it's important that these are synchronized. So the question comes up, well, how do we make sure those are always synchronized? Well, one way to do that would be a mechanical shaft that connects this rotor to that rotor. So they both are connected to the same shaft, so they're both spinning the same. They can't, like, unless something happens to the shaft where it breaks, they would remain synchronized. But notice that that's an impractical solution, because if we're close enough to connect these with a mechanical shaft, we probably don't even really need a communication system. We could just run this switch all the way through to that latch. Why mess around with all this electromechanical nonsense in the middle if we're close enough to connect these mechanically. So that doesn't make sense. The other option would be to tune them carefully, so like a clock, so that this one matches up with that one. But notice that just like with any clock, especially one that's a mechanical device like this, they're going to get off. Over time, one of them is going to be either faster than the other. Even if they're very, very close, they'll eventually get off, and one will slowly creep ahead, and that will be off enough that it won't work, and then we'd have to resynchronize them somehow. Also notice that tuning them and synchronizing them, that concept could be very difficult because they're far apart. The whole idea of this kind of telegraph was to have messages sent over long distance. So how do you make sure the two things are in the same position? Well, you could say, well, you stop them and you put them at, I don't know, like the 12 o'clock position up here, and then you start them at the same time. How do you start them at the same time if that's true? And how do you know that? Well, you could say, well, you call somebody on the telephone, but there was no telephone when these were invented. You might say, okay, well, you set your watches and then you drive apart and then you start it at exactly the same time, but what if those watches are off? And so the question of how do we make sure that these remain synchronized is what we're going to talk about a little bit today. Now, so those two things I mentioned there weren't practical, but what is practical is we said, all right, well, if you could call somebody on the telephone or send a message that says start now, that would be a way to make sure these are always synchronized. You put them in the same position, and then you send them the same start now message, and they both start at the same time. And so then they'll be synchronized at that portion. Now, the idea is, even if those motors aren't perfectly matched, if we were to stop it again and start it again, it would stay synchronized, and you would just have to be roughly close to stay synchronized, imagine, for like 1 revolution. So even if it was off by like, I don't know, 2 or 3% or maybe even 5%, it would stay roughly synchronized throughout 1 revolution. So essentially what Baudot's system did is they added this extra bit. And imagine, notice where it is right now, it's right before bit 1. Imagine that we run a wire from this end to that end, and when a signal comes through that wire, it starts the motors running. And realistically, what happened in the systems that were designed, they actually had a clutch, like a clutch on your car. So what happened is there was a motor constantly running, and when that bit came in, it released the clutch, which now both of them would spin. And then when it got to a bit over here, back to the start position again, when it got back up here, it would disengage the clutch and lock the rotor back in this position again, waiting for the next start bit. So the start bit acts as a resynchronization message that's separate from the data message. So in other words, if we latched the data we wanted into the thing here, and then we hit the start button, the start message would go over here. Our start button would start our motor. The message going through the other end would also start its motor. They would then complete 1 revolution, and then the clutch would disengage, and now we're latched back in the starting position again, waiting for the next start message. And that's a brilliant solution, and actually it's still used today. But the idea is of adding the start bit. It's basically an additional bit that's added at the beginning of each group of character bits. So in other words, that start bit has to be the opposite of the line's idle voltage. So if the line is low, the start bit would be high. If the line idles high, the start bit would be low. And in general practice, the communication lines tend to idle high. And I'm going to ask you why you think that would be. Why would they make communication systems like this idle in the high state? And the answer to that is if you idle in the low voltage state, well, I'll give you a couple seconds to think about it. So why would they make the line idle in the high state generally in communication systems rather than the low state? Especially communication systems that use wires. You can imagine the Jeopardy music playing right now. Okay, if you want, you could pause it and think about it more, but I'm going to go ahead and provide the answer now. And the reason is if it idles in the low state is essentially no voltage. And that means you can't tell the difference between the line being idle and the line being completely broken or disconnected. So essentially the line idling high has 2 purposes. One is it's the idle state, meaning nothing's being sent, but it also says, hey, we're connected. If the line is high, you could have like a little light or something, or you could have a needle, or maybe you put a meter on that or whatever. But you could tell if that's in the high state, you can immediately tell that we're connected. There's just nothing coming through. Whereas if it idled low and the line got broken, you'd say, well, there's no message coming in, but it could be that the line is broken. And as we'll see later on, the line being forced low and being held low is actually called a break condition, specifically for that reason. A break condition is where the line just stays low constantly. The line is broken. Okay, so the line generally idles high, like this. And you'll notice that the start bit now is the opposite state. So this falling edge here is going to indicate the place where the motors get engaged. So the motors get engaged, the rotors start spinning, they go through bit 0, bit 1, bit 2, bit 3, bit 4, and then the line over here goes back to idle. And when that goes back to idle, we're now back waiting for the next start bit. The next one comes in, this falling edge happens, all the bits get latched, 0, 1, 2, 3, 4. In the case of Baudot's 5-unit code, there's 5 slots here. And then after that, and also notice we added this start bit period here. We'll talk about that in just a second, because that's another thing that we need to add. But the falling edge of the start bit engages the motors. Both motors spin all the way around, and they stop back in the idle state waiting for the next start bit. All right, now what's this stop bit doing here? Let's talk about that. So the stop bit that's added to the end does not stop the motors. That's not the point of it. The reason for the stop bit, there's kind of 2 reasons. The main one is that ensures that, and notice the stop bit has a value that's the same as the idle voltage. And in other words, the opposite of the start. So start bit is 0, stop bit has to be 1. And the reason for the stop bit is it doesn't stop the motor, because it's not like it gets a message and it tells it to stop. The reason for the stop bit is it ensures the line goes back to the idle state and has at least 1 bit's width period worth of holding it at the idle state to be prepared for the next start bit. You notice this dotted line here, that would be another start bit starting another message if one existed, but if it's idle, this will just stay in the idle state, in our case high here. Now some systems might have longer stop bit periods, like generally you have to have at least 1 bit, but you might have 1.5 or 2, or you might have even longer period here where the line remains high. But generally, 1 stop bit at least 1 stop bit is required, because we have to return the line back to the idle state, or otherwise we couldn't see the falling edge of the start bit for the next character. And you could see that. So for example, if bit 4 ended up low, and then we put a start bit right against that, and it stayed low, there would be nothing to resync with. We need to go have that transition from idle or high back to low in order for the start bit to resynchronize. So in other words, after the stop bit, the line's idle and immediately ready for the next start bit to come in. And again, you can see that dotted line there. Okay, so let's look at an example of some data being sent using this asynchronous communication method. So let's start out with Baudot's 5-unit code sending the message high. And 5-unit code for high, let's go back and look at the table. So H and I, the table is back a ways. Give me just a second. So H is over here. So 1, 0, 1, 0, 0. And then I is over here. And I is 0, 0, 1, 1, 0. So those are the 2 messages we're going to send. So let's go back forward to where we were, right here. So 1, 0, 1, 0, 0, and 0, 0, 1, 1, 0. Now, in order for these to be sent, we can add the framing bits. So notice over here, I just wrote those on the ends. And that's to make sure you see the whole message that's being sent is going to be always a 0 at the front for the start bit, because our line idle is high. And then the data bits in the middle, and then the stop bit at the end, which is always going to be the opposite of the start bit, which is in this case, the stop bit is a 1. And I've color-coded those green for start, red for stop. But again, the stop bit does not tell the machine to stop. It basically just gives, it ensures that the line returns to high, so the system is ready for the next start bit, and it returns to high for at least 1 bit worth of time. So here's what the entire waveform of that message would look like. The line is idling high. The first start bit comes in. There's a falling edge for start. Now we have the first data bit, 1, 0, 1, 0, 0. So the message, high, low, low. And then our stop bit that returns to the idle state. And notice this idle period could be as long or short as we want it to be because we've stop bit ensured it went high. And then eventually we get to where we want to send the next character. Start bit, 0, 0, 1, 1, 0. Now in this diagram, I've got these little like mountain looking things here. That's realistically the line would probably stay low. I put those there just to act as a divider so you can see where the divisions were. So really this would go from idle to low, and it would stay low, and then go high for 2 periods, and then go low for 1, and then go high for the stop bit, and then back to idle. So these little things here would probably not show up on the waveform. And in the future diagram, you won't see those. But I left them there so you can see the little division periods here more easily. Okay, so the idle sections can be as long or as short as necessary. It could even be the start bit for the next message happens right after the stop bit is done, immediately starts. Or it could be the idle period goes on for, I don't know, 10 minutes or an hour or a day. Because what synchronizes the motors again is the next start bit at the beginning of each message. So the start resynchronizes, the start bit resynchronizes, the stop bit ensures the line is returned to idle to be ready for the next start bit. All right, very clever system, still used today for asynchronous serial communication. And asynchronous, let's talk about that for just a second. Asynchronous means, synchronous means with respect to some clock. So in other words, you have some clock, you're both using the same clock, you're synchronizing your actions based on the ticking of that clock. Asynchronous means the A in the front means not with respect to time, or not with respect to a clock. Now that's a little bit of a misnomer, because notice there's still timing involved here. It's, so what's called asynchronous is basically just saying, well, they don't have to have the same shared clock. They're not using the same identical clock source or a physical shaft that they're both connected to. There can actually be some variation in those two motors and how fast they go. Timing doesn't matter with those, except that they have to be roughly the same to get us through one entire group of bits without it drifting so far off that we're now on the wrong bit when we sample the data. So asynchronous is not really truly asynchronous. Asynchronous here is we still have a clock, but they each have their own clock. They're not sharing one. And it's resynchronized at the beginning of every message to make sure it doesn't get off. So it's kind of like synchronous with a resynchronization pulse at the beginning. But it's called, in the terminology in communication, it's called asynchronous. Okay, so stop ensures the line returns to idle. Start does the resynchronization. And then the data bits are sandwiched between the two. Okay, a few more definitions here that I want to put up. The first one is baud rate. Baud rate is a term that is the number of changes made to the channel per second. It's also sometimes called the signaling rate. So the baud rate of a connection, like a serial communication connection or any kind of connection, the baud rate or signaling rate is the number of changes that are made to the channel per second. That's named after Emile Baudot, the creator of that Baudot 5-unit code and the systems associated with that. And the data rate, the number of bits, is the number of bits encoded per second. In other words, sometimes the baud rate and the data rate don't match. And in fact, let's go back here. The baud rate and the data rate of these don't quite match, because the baud rate is how many changes are made to the line per second maximum. So in other words, this would be a change, that would be a change, that would be one, that would be one, that would be one, this would be one, even though it stayed the same voltage, it's still a potential for a change. And so the baud rate is how many changes per line per second. But the data rate is how much data we're pushing through there. And you'll notice here, we have two of these bits that aren't data. Start bit, stop bit. Those aren't data that's being passed through. Those are framing bits. They're not part of the message. They're things that were added just for transfer. So in this case, our data rate is going to be slightly lower than our baud rate. Okay, so sometimes the data rate and baud rate are the same. Sometimes there are systems too that encode more than 1 bit for every change in the line. For example, there are a number of examples like that, like the cell phone data communication has a different way of encoding the data. It encodes more bits, and sometimes it's much lower. So for example, LoRa, long-range wireless communication systems, they encode the data in a way that has a whole bunch of redundancy. So even if parts of it get messed up, it pulls it back, but the data rate for those is very low, but the signaling rate can be much higher for those. All right, also framing bits, I use that term, but those are the extra bits that are added around the data that combine to form a serial data unit. So a serial data unit consists of the start bit, the data, and the stop bits, but the framing bits of that serial data unit are the start bit and the stop bit. And there might be a parity bit. We'll talk more about parity later when we get to the part of this class where we talk about error correction and error detection. Parity is a form of error detection. It's a simplistic form. We'll talk about it. All right, asynchronous serial communication is, again, using that time division multiplexing to transfer a serial data unit of data 1 bit at a time in a case where we have a start bit and a stop bit. All right, so notice that we can use that method to send serial data units that have more than 5 bits of data. The original Baudot system only had 5 bits of data, but there's no reason why we couldn't use that to send something with more bits of data than 5. So the only real limitation on how much data we could put between a start and a stop bit is both ends have to agree upon that ahead of time and have the hardware to handle that ahead of time. And the other thing is the clocks have to be able to be close enough that they remain synchronized for the duration of once the start bit starts. We have to be able to have the timing be close enough that we're on bit 7 or bit whatever it is, but at the same time they are when we get to the end. If the clocks are wildly varying or different, then we could get to the end and have them be off enough that it would corrupt the data. All right, so here's an example of a serial data unit that has the 8-bit ASCII character capital A. So it's actually, ASCII itself was a 7-bit code, but in computers we usually think of bytes as 8 bits. So I put the 8-bit representation here. And actually, I've got these bits labeled backwards because I'm putting the... I should probably flip that around. So this is the kind of the, we're going most significant bit first. That should be bit 7, working our way down to bit 0. Or I should invert the data to match. So there should be a 1 here, and that should be 0. But anyway, I think you get the idea that it works just like Baudot's 5-unit code in that we send a bit, send another bit, the data bits sandwiched between the start and the stop. And so essentially that ASCII capital A looks like 0, 1, 0, 0, 0, 0, 0, 1. And here's 0, 1, 0, 0, 0, 0, 0, 1. Now, since time is going that way, it depends on whether you're sending the most significant bit first or the least significant bit first. I should probably fix that diagram. I'll fix that later. Let's just get through the rest of the lecture. There's not too much left today, so let me just get through the rest of that. But just note that it depends on whether the system is sending the most significant first and working its way toward the least, or sending the least significant bit first and then working its way toward the most. Generally, it's the least to most, so my diagram that I made is actually a little bit backwards. This should be a 1 here. That should be a 0 here. Actually, let me go ahead and fix that. I'm going to fix it and be right back. Hold on 1 second. Okay, so I just solved this the easy way and made these go from most significant to least. But realistically, in a lot of systems, it would go least to most, and so that would be backwards. I just did it most to least, so it would match this pattern to make this a little more clear. Since we read from left to right, I made this kind of match that. Realistically, it would probably go across the line in a reverse order with the least significant bit first, going to most. But as long as both ends agree on their way of encoding that and decoding it, then the same message would work because each bit is just given its own time slice. So realistically, we'd probably have 1 and then 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. But in our case, just to make it clearer that that's what's being sent, there it is. So we're going from this way, that way, rather than that way, that way. Anyway, looking at the next slide, the serial data unit containing the 8-bit ASCII character looks like this. And the thing to note here is that that entire thing is a serial data unit. So the entire thing, the start bit, the data bits, and the stop bit, that's a serial data unit. The start and stop bits are called framing bits. The message portion between the start and stop bit are called the data bits. Some systems have more or less data bits, like Baudot's system only had 5. Some systems have 7, some have 8, some have 9. I suppose you could have other larger numbers of bits or smaller numbers of bits. It depends on the thing, but the whole idea of asynchronous serial is we resynchronize with the start bit, we then start into our data bits, and when we get to the end, we have a stop bit, which ensures that it returns the line back to idle. Also, some systems have a parity bit added in before the stop bit that's used for error detection. We'll talk about error detection in a future lecture. Okay, so modern asynchronous serial. Baudot's system used this a long time ago, back in the 1800s. But fast forward today, modern systems still use this kind of communication. They no longer use mechanical rotating multiplexers as in Baudot's time. So it's not when you're sending serial data out of a serial port from a computer or device, there's not like a mechanical thing in there clicking around little switches. But the concept is the same. The data, if you were to put a meter on it or a scope, it would look the same kind of thing like this. And we're actually going to look at some of that data later on in the class. All right, so, or at least later on in the semester. So modern systems no longer use rotating mechanical multiplexers, but they use the same methodology. So modern systems actually use electronic multiplexers, and they use a special kind of integrated circuit called a Uart. And what a Uart is, Uart stands for universal, asynchronous, receiver, transmitter. So in other words, a Uart universal means that it can be programmed to go at different speeds with different data formats, different numbers of data bits, different numbers of stop bits, different baud rates for how often it pushes the bits out onto the line. So that's what universal stands for. Asynchronous means that it has those framing bits, a start bit to resynchronize for each serial data unit. And then receiver transmitter means it has both a receiver inside of it and a transmitter inside of it. So we're going to look at UARTs in more detail in a later lecture as well. And notice that there is a way to implement the multiplexing in software only. So rather than having a special chip or a special piece of hardware, we could actually implement that in software with an algorithm or a program to do that. And if it is implemented in software, that method of asynchronous serial communication is called bit banging. And bit banging basically means you're taking a bit, putting it out on a single I/O line, and then waiting a little bit. And then you take the next bit, bang it out to the I/O line. So it's kind of like chucking the bits out one at a time through code that's written. And on the receiving end, it means you have code that's kind of waiting for the start bit. When it sees the start bit, it waits a while, pulls the data off the line or reads the I/O line, waits a little while, one bit width with a period, reads the next one, and so forth all the way to the end. So you can actually solve that both ways. Now, if you are using bit banging, then you can't really get quite the high rates you could get with something like a UART as easily, because the UART, the hardware is handling the timing and the clocks and everything, so the computer doesn't have to. But if you're doing it in software, the timing between those bits becomes very important. So you either have to do that with some sort of timer interrupts, or you need to do that with some sort of high resolution timer to make sure semi-high resolution timer, depending on what rate you're going. And you need to make sure other interrupts don't affect that timing or other things in the program don't affect that timing in some way. So it becomes important to write that code pretty well to get higher data rates on bit-banged serial communication systems. And like I said, we're going to talk more about UARTs in a later lecture. We're actually going to write some code and look at some waveforms coming out of the UARTs. You're going to actually implement your own bit-bang algorithm or program to push data out over one of these asynchronous serial things. Now, one thing about what we've talked about today is that this stuff, like I said, even though it was invented in the 1800s, it's still used today. When you talk to something over a serial port, a serial connection, it uses that UART. In fact, the Arduinos that we're going to use in this class, the way they talk to the computer is through USB, but there's a special chip that converts the USB signal into asynchronous serial signal to talk to the microprocessor on those boards. So this stuff is still used, even though it was like the first form of time division multiplexing that was used, invented by Baudot in the 1800s. This is still used today because it makes sense. It's a really clever way to have one line share a lot of data. And actually the same kind of thing is used in wireless systems. It's just rather than time division multiplexing sharing a single wire, they're sharing a frequency band to put data out over a wireless system in that. So if you see the kind of TDM associated with some kind of wireless system, time division multiplexing, just note that it's dividing up the message into bits. It's putting each bit into the wireless spectrum one at a time to form larger messages from that. There are other methods for encoding the data as well that we're going to see going forward, but that's it. Now, last thing, make sure to complete Lab 0, which was that little help me get to know you thing where you just submit a PDF file with a picture of yourself and some questions answered. But Lab 1 is what I want to talk about now. So let's take a quick look at Lab 1. I'm going to pause this for a second while I switch this over so you can see Lab 1. Okay, so here's the lab sheet for Lab 1. And for Lab 1, what I want you to do is order the parts that you're going to need to do the labs for the first 6 weeks or so of the class. Maybe 7 weeks. And there's no textbook for this class, so essentially the materials you need will be relatively inexpensive, and if you have somebody you can work with on the labs, like a roommate that's in the class, or maybe some friends that are in the class, you could split up the cost of some of this if you needed to. But I would do want everybody to order at least one Arduino to have for yourself if you don't already have one, and I want everybody to order one of the other things as well for yourself. If you want to stay safe and are working remotely, just get 2 of them. There are other materials that are going to be used in this class, like little wireless modules that we're going to communicate with. I'll make those available and hand them out to you later on when we get to that point. But for right now, this is what you need to get. So let's go and take a quick look at it. For first thing here is you're going to need 2 Arduino Uno R3 kits. And those look like this. These are the ones that I got off of Amazon. They had the Elegoo brand. They're not the official Arduino, but Arduino is an open source hardware project. So other companies make them and they work. So feel free to look at other companies' versions of these on Amazon. The original Arduino ones are a little bit more expensive. So if you want an original one, feel free to get it, but these ones cost about $14 a piece. And let me explain quickly what they are. What this is what's called a microcontroller. It's a whole computer system on a chip. It's actually not a super powerful, like multi-core processor like would be in a cell phone or a Raspberry Pi or something like that, but it's a microcontroller that's still pretty powerful. It's a 16 megahertz processor that's a RISC architecture, so this can do 16 million instructions per second, and it's designed for embedded systems. This little chip up here is the USB to Uart converter, so we can talk to that chip and program it. But essentially, these come as a kit that comes with a cable which also powers this thing. And you just plug it into your computer, and then there's some free software you can download, kind of the Arduino development environment you can download and install. And you'll be able to write programs and put them on here and run those programs. That's what we're going to do for the first several labs for this class. Really probably up through the next 6 weeks or so. Now, so you don't have to buy any software. That's free and open source. And really, feel free to shop around and find these at a cheaper price if you want to. But the ones that I bought were these Elegoo ones from Amazon, and they work fine. They're actually pretty high quality, and they work well. The other nice thing I like about these, other than some cheaper ones, is notice that the pins are labeled on the plastic header connector here. Which makes it easier to do the wiring. It's labeled actually on both sides of this, so it's easy to see. I have had some cheaper ones of these, cost a few dollars less, but the black plastic here is not labeled at all. It's labeled on the board, but not on the plastic, so it can be more confusing when you're wiring them up. All right, the next thing you're going to need is this Dupont Cable Kit, which this paginated this funny. I'll fix that when I post it to the course page. But notice the Dupont Cable Kit. Dupont cables are... I usually have some of these sitting around near me, but here's some. Essentially, Dupont cables are these cables that have these little black plastic connectors on them, and they're what the Dupont cable that costs $7, and you get 120 different varieties of these, and they're all made in these rainbow colors, so it's easy to tell which one goes to where on the other end. And these also can be split, so you can actually peel off those. So you basically get 40 of each of these varieties. Female to female, male to female, male to male, which covers anything that we're going to hook up in this class. And those are relatively inexpensive, very useful for development, but I would go ahead and get one kit of those as well. And these are also Elegoo branded. You can get ones from another brand, maybe a little bit cheaper, but these are the ones that I got. The last thing that you're going to need to get is this ESP WROOM32 development board. This is also Arduino compatible. You can program this with the Arduino environment. And for $11, you get a really high power processor / wireless module all built into this. And on board here is a little USB to Uart Converter, the little chip that's necessary to program this. And so these are actually real powerful, and these actually can get on Wi-Fi systems. So I would go ahead and get these things here. If you wanted to save a little money right now and get this later, I'd get it later, but I'd just go ahead and get it now. It's $11. But what you're going to do is you're going to order those things, and I want you to have those for next week because we're going to start on labs doing stuff with these next week. So go ahead and get those ordered sometime this week. Hopefully today or tomorrow. And the way you're going to submit your result for the lab is make the order, take a screenshot of it, or of the order, or take a picture of it with your phone or whatever, and then submit that on the submission thing. If you're planning to work with somebody else and are ordering a single Arduino, or you already have one, tell me that in the comments and who you're working with. And I just want to make sure that you have available for the lab for next week 2 Arduino boards. Either you already have one, or you and a friend have one together, and you have these Dupont cables to be able to wire and hook them up, because that's what we're going to be doing next week. So next week what we're going to actually do is we're going to take 2 of these little computer boards, and we're going to connect them with wires, and we're going to get them to talk to each other and kind of build up our own kind of experimentation platform for writing some of this code to do things like time division multiplexing. The first lab is going to be simple. It's just going to be establishing a channel where we change the value on one board, the pin on one board, it goes to the other. Now, quick thing about Arduinos is the language that's used to program these is C++, which is a superset of C. So a lot of the stuff you learned in systems programming or data structures is going to become useful here, because that's how we're going to program these chips. There are some versions of embedded boards like this that use a thing called CircuitPython. We're going to use C and C++ to write the code for these guys. I believe this thing actually has both a C environment and a CircuitPython that you can use on that. But we're going to use C and C++ for most of the stuff in here. So if you are a little fuzzy on that, maybe go back and familiarize yourself with C and C++ programming, especially bitwise operators. We're going to be doing some stuff with those this semester. All right, so that's it. Work on that lab 1 and lab 0. Let me switch back to the presentation for just a second. So work on lab 0 and lab 1. Stay safe, wash your hands. If you're around people outside of your immediate household, wear a mask. And what we're going to do next class is you're going to have some time to work on those labs and get those labs done. Or not these labs, but the new lab that we're going to have next week. Because we're going to dig in pretty quickly into actually making things communicate. So like I said in the first lecture, this is going to be part theoretical stuff, and it's also going to be part hands-on doing stuff, and that includes actually getting things to communicate. So we're going to wire things up, make them talk to each other. We're going to write the code that does that. All right, that's it for today. Everybody stay safe, and next time we're going to get started. Get those boards ordered, and if you are having issues with anything, be sure to send me a text message or an email, or give me a phone call. Just let me know, and I'll do what I can to help. All right, that's it for today. Bye.